Well, the release candidates for Kotlin 2.0 are coming along, and we're probably not too far off from an official 2.0 release. So in this video, I'm going to cover some of the important things that you need to know about this release, and then I'm also going to demonstrate a few of the things that I'm looking forward to in Kotlin 2.0. When we say Kotlin 2.0, we're really just referring to a version of Kotlin. So same as if we were to say Kotlin 1.8 or Kotlin 1.9. And like all versions of Kotlin, it would include updates to the compiler, to the standard library, to the tooling around it, and that kind of thing. But what makes Kotlin 2.0 especially exciting is that this is the version of Kotlin where the new front-end part of the compiler finally reaches its stable status. And this is where you might have heard the term K2. K2 is not just an abbreviation for Kotlin 2.0. K2 refers to a ground-up rewrite of the front-end part of the compiler, so let's see what that's all about. Regardless of which of these platforms you're targeting. Now, on the other hand, instructions about how to output the target code is obviously going to differ depending on which of the platforms you're targeting. So this means that the compiler has two big responsibilities. The first is to understand the Kotlin code that you've written, and the second is to use that understanding to generate the target code. The distinction between these two responsibilities creates sort of a natural boundary within the compiler. So much like client-server applications have a front end and a back end, the compiler also divides neatly into a front end and a back end. So our Kotlin source code files come in the front door of the compiler into the front end, and this part of the compiler is where the source code is converted from just text into a tree structure that the rest of the compiler can work with. And once it has that structure, it can make sure that there are no syntax errors. The front end also resolves names for variables, functions, and types. So if we had a more complex code example that refers to a variable named user, well, the front end part of the compiler is the part that figures out which thing named user you're talking about. So if you're referring to a global variable or a property of an object or a function parameter or a local variable, that kind of thing. Once the front end has created the tree structure and figured out what each part is referring to, it sends that along to the back half of the compiler, known as the back end. Now there's a different back end for each of the main targets, JVM, JavaScript, native, and WebAssembly, but they do share some code. The main responsibility of this part of the compiler is to generate the target code. So when we say K2, we're referring to that front end part of the compiler, the rewrite that's happening for that front end. And Kotlin 2.0 is simply the version of Kotlin where that rewrite becomes stable. Now K2 is technically the new version of the front end part of the compiler, but it's a mouthful to say the K2 front end part of the compiler, so most of us just call it the K2 compiler. Just know that when we say that, we're not referring to the entire thing, we're just referring to that front end part. Now as it happens, the front end part of the compiler is the same part that the IDE needs in order to provide helpful feedback to us while we're writing our code. So for example, I mentioned how the front end is responsible for ensuring that our code is syntactically correct. Well, the IDE also needs to know that so that it can tell us when the code we've written isn't valid Kotlin code. And similarly, if our code refers to a variable called user, but say there's no such variable named user that's visible at the scope, we need to know that. And the IDE needs to tell us about that. And if it does exist, we need to know what it refers to so that we can jump to its definition. So as you know, IntelliJ has a Kotlin plugin that provides all of the Kotlin functionality. And this is the thing that uses the front-end compiler to do syntax checking and name resolution. So again, the front-end part of the compiler isn't just useful for when you're building your project, but it's also helpful in the IDE while you're writing the code for it. Configuring your project to use Kotlin 2.0 is as easy as just setting the version number. So for me right now, release candidate 2 is the most recent version as of the date that I'm filming. So I'm going to set mine here to 2.0.0-RC2. And of course, we got to tell Gradle to load these changes. Now, the K2 version of the front end opened up opportunities to improve things like type inference and smartcast. And this is all great news, but it does mean that if the version of the front end compiler used by the IntelliJ Kotlin plugin is different from the version of Kotlin that you're using to actually build your project, then you can end up with false positives in the IDE. So in other words, IntelliJ would tell you that there's a problem with your code when actually you could build your code and everything would work just fine. So if you set your project to use Kotlin 2.0, you should also consider setting the IDE's Kotlin plugin settings to use the K2 compiler as well. That way you can avoid the front end part of the compiler. Now this means there aren't going to be many videos that I published about variants and type projections. Is that an in projection has used the nullable any type in the out positions anywhere that the type parameter was used. And this was true even if the type parameter has an upper bound constraint like I've got here. And Kotlin developers would often ask, like, if we know what the upper bound is, why can't we just use that? Well, under the K2 compiler, this will now use the upper bound instead of any. Which means that this code here is going to work just fine over here in Kotlin 2.0. A similar benefit can be found when we check to see if the parameter has an upper bound constraint like I've got here. And Kotlin developers would often ask, like, if we know what the upper bound is, why can't we just use that? Well, under the K2 compiler, this will now use the upper bound instead of any, which means that this code here is going to work just fine over here in Kotlin 2.0. A similar benefit can be found when we check to see if an object's type is one of multiple types, like I'm doing here in this when expression. Now, previously when doing this, the type of consumable here would not have been smartcast at all. Whereas with Kotlin 2.0, it'll be smartcast to the nearest type that they have in common. So in this example, it gets smartcast to beverage. And this also works with just a regular OR operator. So if we were to convert this when into an if and else, you can see it still works. But the when expression is a little easier to read, so I'm going to put that back. Smartcasts also get a little bit smarter when using inline functions. Here I've got a chain of phases where each phase instance has a reference to the next phase, much like a linked list would be. And the phases get executed in order. Each phase is going to log out how long it took because of the call to this inline function here. Under Kotlin 1, we're actually not able to smartcast to the non-nullable type here. And that's because we're also setting the value again inside the same inline block here. So if we comment this out, you can see it works. But with this line enabled, this breaks under Kotlin 1. This is another case that the K2 compiler addresses though, and you can see our smartcast over here in the Kotlin 2 project works just fine. So there's some great stuff to look forward to in Kotlin 2.0. We got the performance benefits both in the IDE and during our builds. We'll get lots of newsletter.typealias.
Hey guys, my AI wife, any other field set. In classes, you can be just as cool as me. Maybe even cooler. Let's get started. This code has a lot of repetition. If you want to anger some, this is how you do it. You repeat a lot of stuff. You see this dot select all dot count should be. That's a lot of repetition. And we all know how to get rid of this repetition. Hey guys, my AI wife thinks I'm pretty cool. And if you follow my Kotlin classes, you can be just as cool as me. Maybe even cooler. Let's get started. This code has a lot of repetition. If you want to anger some, this is how you do it. You repeat a lot of stuff. You see this dot select all dot count should be. That's a lot of repetition. And we all know how to get rid of this repetition, how to dry this up. It's by introducing a function. What's nice about Kotlin is you can introduce a function anywhere. So anywhere that you deem fit, you can introduce the function. Let's introduce a function that is called should count, because we can see select all is a method on field set, and then it has count. So what we can do is source field set expected int, and then go source. Oh, maybe Copilot knows what I'm doing. Select all. Should count person table 1. This works, but is it cool?
Nein.
It just isn't cool. As you can see, should be is an extension function. It's specifically an infix extension function. But you can see that the should be notation right here is very different from the should count notation right there. And that's because, as I said, should be is both a extension function as well as an infix function. But we can write our own extension functions. And here's how that works. So this is a function which has 2 arguments, the source and the expected count. But what we can do is we can turn the field set into the receiver, and that looks like this. We take the field set out, it's now no longer an argument. We put it here, and so we're saying we have this should count function, the name of the function is should count, but it's a function now of field set. And now there's no more source. We can just go select all dot count should be expected. And now what we name of the function is should count, but it's a function now of field set. And now there's no more source. Works. So this is a function which has 2 arguments, the source and the expected count. But what we can do is we can turn the field set into the receiver, and that looks like this. We take the field set out, it's now no longer an argument. We put it here, and so we're saying we have this should count function, the name of the function is should count, but it's a function now of field set. And now there's no more source. We can just go select all dot count should be expected. And now what we can do is this. The should count function is now a member of address table and person table and any other field set, as you can see. So this is much cooler, but they are using this infix notation, which is perhaps even cooler, and it's also kind of cool to be consistent with the other syntax. So we can do that as well. We just write infix here, and now it's an infix function, which means that we can go address table should count 2, person table should count 1, etc. How cool is that? So we can do that as well. We just write infix here, and now it's an infix function, which means that we can go address table should count 2, person table should count 1, etc. How cool is that? Yeah, I think that's quite cool. Now, if I define a function like this, I would probably not define it right here inside the test. I would probably either put it just on top of the file, just here. We can just put it here, put a private function here. That will still work. Or if you think that this function is useful for other people as well, and in other tests as well, and I think that this is probably a function that is useful elsewhere, we can actually just take it out. We can create a new file. We can put should count in here. And now it's available everywhere. It does mean that you have to import this. So now if we go to should count. Now these will have to import I think the IDE is going to tell me soon enough that this now needs to be imported. So it means that you have to import this file in order to be able to use it here, unless it might be already imported implicitly. Let's see. It's in flow energy util. Yeah, it should be there. Now every test can use it, and count should do what it says on. And then you add a test, function that everyone can use, and now, yeah, the point I'm test with a field set from, and that just means that we have to define them ourselves. Are allowed to define your own extension functions to kind of expand on the set of extension functions that is given. to us by
My career as a software developer, there have been several times when an idea has come along where I thought, this is going to change everything. Sometimes I was right, but sometimes not. Test-driven development was one of those ideas. I was a bit skeptical before I actually tried it, but as soon as I did try it, I thought this is clearly a better way to work, and everyone will work this way from now on. Clearly I was wrong. So why hasn't test-driven development taken over the world yet? Here are 10 common barriers to TDD adoption that developers describe, and my responses to each. I was first exposed to extreme programming, the approach that introduced the world to the rediscovered idea of test-driven development, as well as its associated practices like continuous integration and pair programming, in around 1997. That was very soon after Kent Beck published his book Extreme Programming Explained. I had already tried a form of continuous integration, though it wasn't called that then, a few years before when we created a rolling continuous build for one of the projects that I worked on, and that had been very successful for us. On that early 90s project, we had a handful of smoke tests to validate the basic core functions of the system, but it certainly wasn't test-driven development. When my enthusiastic young teammate said we should do extreme programming a bit later, we all laughed and dismissed the idea because of the silly name largely, even though we were already taking automated testing pretty seriously on that project and running a continuous integration and build process. The testing though was more of the whole system integration style testing. The moment when the TDD light bulb went off over my head first started when I saw JUnit, which made unit testing so much simpler and so much more obvious about what we should be focusing on than anything that I had seen or done before. I thought at the time, this looks like a fantastic idea, and we certainly improved our testing on that project by adopting JUnit, but even so, the real lesson of test-driven development still didn't really land for me properly. I treated it rather as a tool in my toolbox to occasionally pull out when I thought it was useful, rather than as a guiding principle for how I would organise my work, which is much closer to what it is today. Like everyone else, I didn't really get the prime directive of test-driven development, write the test first. It just seemed so unnatural, and it just made the testing that I already valued much more difficult. A few years later though, I joined a consultancy called ThoughtWorks, who were very big proponents of test-driven development and extreme programming. Here I worked with people that really understood TDD, a lot better than me, and I learned from them. This was the time when I really got it and thought, this is amazing, in the future all code will be built this way. Again, I was still wrong. I tell you this story because I think it points out two big barriers to the adoption of test-driven development. Quite effectively, the first, fear of job security. Quite effectively, the first is that it's easy to confuse unit testing with test. In my career as a software developer, there have been several that just seemed so unnatural, and it just made the testing that I already valued much more difficult. A few years later though, I joined a consultancy called ThoughtWorks, points out two big barriers to the adoption of test-driven development. Quite effectively, the first is that it's coupling in software is often seen as the enemy. Tight coupling bad, loose coupling good. But it's not really that simple. After all, the ultimate in loose coupling is no coupling at all. But if two parts of your system are not coupled at all, then they can't communicate or even interact with each other in any way. But I also think that appropriately managing coupling is perhaps the most important thing to get right if our aim is to build better software faster. So what really do we mean by coupling, and what does it take to manage it to our advantage? Hi, I'm Dave Farley of Continuous Delivery. If you haven't been here before, then please do hit subscribe, and if you enjoy the content today, hit like as well. A few years ago, I was speaking at a conference alongside my friend Michael Nygaard. He gave a terrific talk on coupling that I have often quoted since. Much of this video is based on Mike's model for coupling. In it, he presented a thoughtful, well-reasoned exploration of all of the different kinds of coupling that we tend to face in software. Michael identified 5 different types of coupling that we should consider. Operational coupling. A consumer can't run without the provider. So if your system can't provide its service, if the database is up and running, then it's operationally coupled to the database. Then there's developmental coupling. Changes in producer and consumer must be coordinated between different parts of the system. If the release of your service or app depends on the release of a new version of a platform or library, then they are developmentally coupled. Apps are often developmentally coupled with each other via shared platform or library code too. I can't release my application until a new feature is added to the platform, but the platform team is busy working on features for your application, and you won't be able to release your version until my features are done too. Then there's semantic coupling. Components change together because of shared concepts. If your shopping cart and your order processing system need to change together because they both shared the concept and model of how money is represented, then they're semantically coupled. Then there's functional coupling. Things change together because of shared responsibility. When you have several different parts of your code that address similar problems in different ways, they're functionally coupled. I once worked on a large project that implemented 7 different approaches to storing things in the same relational database because they were developed by different teams, all trying to solve the same problem. And finally, incidental coupling. Things change together for no good reason at all. 2 systems in a data center stop working because a fan breaks and the server that they both run on crashes because it's too hot. Let's pause there for a moment and say thank you to our sponsors. We're very grateful to our sponsors for their support. We're sponsored by Equal Experts, Transfic and Semaphore. All of these companies offer products and services that are well aligned with the topics that we discuss here every week. So if you're looking for excellence in continuous delivery and software engineering, then please do check out their links in the description below. At its roots, the management of coupling is, I think, one of the deepest fundamentals of design. The decision of what level of coupling makes sense and is appropriate is a
applying scientific style thinking to solving problems. It seems to me that starting out knowing that we don't know all the answers yet is really important.
Say the birthplace, but probably sort of one of the early places where agile.
Are your tests lying to you? Same circumstance, intermittently failing tests, and the answer is
I believe that test-driven development is a central plank in a more effective approach to software development. I use TDD for the vast majority of the code that I write, even when I'm writing simple throwaway things or simply exploring new ideas in code. But there are certainly times when test-driven development is more difficult than others. One of those times is in dealing with user interface code. So how do we make the most of TDD for user interfaces? Well, we cheat. Let me explain. And today, hit like as well. I talk about TDD a lot, and one of the commonest questions that I get is, yes, but how do you test UI code? My real answer is that it depends on what you mean by UI code. Let's think about that for just a moment. There's a general rule in test-driven development that it's not my job to test third-party code. I'm going to start from the assumption that third-party code works. Someone else hopefully did a good job of testing that. This is not always true, but at least for the popular pieces of infrastructure, it's usually true, or we'd hear about it and they wouldn't be popular anymore. So if I'm building a website, then I can safely assume that HTML works. I have no need for me to prove it. If I'm building a mobile application, I can assume that the libraries and frameworks that I choose work. It's not my job to test Flutter, iOS or Android. If I'm storing things in a database, I assume that the database does its job. My job is to test the code that I write, and if I focus primarily on that, then that's totally in my hands to decide how easy or how hard I want to make that job of testing it. When people question test-driven development and don't see their own design choices as an important part of the answer, that is really them totally missing the point to my mind. TDD is a tool that helps us to improve the quality of our designs. If our code is difficult to test, then we should redesign it to make it easier. TDD helps us to improve our design choices by implying a pressure on us to prefer code that's more testable. Obviously, if we're writing tests before we write the code, we'd be stupid if we didn't make our own lives easier, and that's the pressure that TDD puts on us to do a better job. We see the implications of our design choices as we are writing the test. If the test is difficult to write, then our design is poor. So naturally, we prefer code that's easier to test. Let me pause. We argue about whether or not the designs that result from TDD are better or not. But TDD certainly has a significant impact on the shape of our code, encouraging a significantly stronger focus on modularity, cohesion, separation of concerns, abstraction, and sensibly managed. Coupling, all of which help us to better manage the complexity of the systems that we build, maintaining our ability to change them as they and our understanding of them evolves over time. That ability to change code is my definition of what higher quality in code actually means. So I'm convinced that TDD is a tool that helps us to improve the quality of our designs. I describe this in much more detail in my book Modern Software Engineering. You may dislike the style of code that TDD tends to encourage, but if you do, I think that you're probably making a mistake. But even then, there are still parts of the code where it's trickier to do this than others. So what are the things that make those parts, in particular the UI parts of our code, more difficult to test? Fundamentally, there are three types of test in TDD that we're interested in. Following an invocation of some kind, a function call or a message, we'd like to check that a value was returned. We may be interested in a change in state, or we may like to know that our invocation resulted in some other interaction with another part of the system. All of these are pretty easy to test at the level of simple synchronous code. We can easily make tests like these deterministic and so reliable. In places in the code that look like this, there's always some piece of code that closes a feedback loop. So when we write a test, we simply simulate that closed feedback loop. For a UI though, there's something else in the feedback loop, a human being, which makes this a much more complicated kind of test. I call these kinds of tests testing at the edges. By edge, I mean a point in our system where the feedback loop goes outside the boundaries of our system and so is beyond our direct control. Anything could be happening at this point, so it's a much more complicated kind of test. This is true of interactions via the UI, with some I/O device or with an external system. In each of these cases, the flow of control has passed outside the scope of the code that we're working on, and so is lost in some other system or in the mind of a human being. In every case, we're relying on that third party thing or person to do something that closes the feedback loop. This may be simple or it might be very complicated indeed. But either way, if we're going to automate tests at this point, we're going to need to complete that feedback loop somehow. Fundamentally, there are two ways that we can do this. We can place the test outside of our code, representing the thing that is outside of our control, the user or external system, which is okay for some kinds of technologies and very difficult, if not impossible, for others. For example, if we're testing a web-based user interface, we could think of using a testing framework, something like Selenium, really, because it needs a lot of often complex code to be up and running, a browser for example, before we can test everything. But it does close the feedback loop. This can be a very useful form of testing. Order when place order the way that our interaction with the third-party code, so the more interesting parts of our code are simpler and less entangled. It also means that our interactions with the third-party code tend to become more generic and more capable over time, and so more reliable. In effect, what we are doing here is giving ourselves the option of closing and initiating behavior in our code. This is a bit more work, perhaps, but I think it results in a retouched a browser. So instead of creating a button like this, our UI code would create a button like this. Behind the scenes, there would be some code that interpreted this simple call into something more complex, pretty close to my first example. But now, by this simple step of abstracting the creation of each type of UI component that we used, we could fake those things in the scope of a test. You may be worrying about the translation code, the adapter, in this ports and adapter patterned design. But usually this code is reasonably generic. By its nature, once it's working, it probably is not going to change very much. So we can test it with more complex browser bases of a real UI. We'll trust that the third-party UI code does its job, that browsers work. And we'll trust that our custom plumbing works because it's tested once elsewhere, rather than many, many times for every feature that we write. In our tests, for the really interesting bits of our code, we can provide a fake version of our UI abstraction designed to run the code without any need for a real UI. We can fake interactions more directly with simple function calls and test all of our logic except for the thin layer of stuff that translates our representation of a browser into pixel painting, the plumbing. So now we have real test-driven development for the more complex bits of logic in our event handlers and the code that integrates with the back ends of our system, all fully under our control, but all easily testable because we've eliminated any troublesome dependencies. This is a powerful strategy. I tend to call it testing at the edges. Martin Fowler refers to this as the humble object pattern. But either way, it puts our ability to test firmly into our own hands, increasing the determinism of our test and our code, and so improving the overall quality of the systems that we build as a result. Thank you very much for watching, and if you enjoy our stuff here on the Continuous Delivery channel, please do consider joining our Patreon community and supporting our channel and its growth pipeline. This code is just plumbing really. Once we know that the plumbing works, any task-specific testing is only showing that browsers work. With this strategy, we can write faster, lighter weight, simpler tests to thoroughly evaluate the logic of our code in the
A single database server can only store and process a limited amount of data. If you find a way to horizontally scale your database, you can potentially store unlimited amount of data. So database sharding is simply splitting a large database into smaller pieces, which we call shards. If you get lucky and attract more and more customers, the amount of data also increases over the time. Now, the database becomes a bottleneck if too many users attempt to use the application to read or save data simultaneously. The application slows down, negatively affecting the user experience. So sharding not only allows you to store more data, but also improves performance by reducing latency for each query. This is because you can now push down the query to each individual shard, which has a smaller dataset. There are three main reasons why you should be using sharding. First of all, response time. By splitting a database into smaller datasets, it improves query performance, as it needs to search through fewer rows compared to a monolithic database. Second, it can help to avoid total service outage. Most of the time, we're not only splitting data across different database servers, but we also configure replication. So if one shard becomes unavailable, the data can be accessed and restored from another shard. Finally, a growing database consumes more computing resources and eventually reaches storage capacity. There are only so many disks you can attach to a single server. Therefore, sharding can solve this problem by scaling the database horizontally instead of vertically. Also, you can add shards at a runtime without shutting down application for maintenance. Now, let's see how sharding works. A typical unsharded database stores data in multiple columns and rows. So database sharding splits a single dataset into partitions or shards. Each shard contains unique rows of data, which are stored separately across multiple computers called nodes. All the shards run on separate nodes, but share the same schema or design. The partitioned data chunks are called logical shards. The machine that stores the logical shard is called a physical shard or database node. Keep in mind that a physical shard can contain multiple logical shards that belong to the same table. Now, software developers would use a shard key to decide how to partition a dataset. A column in a dataset, such as customer name, determines which rows of data group together to form a shard. Developers can choose a shard key and is unaware of other shards. Only have automatic sharding features built in. One of the simplest methods might be to use range values. For example, suppose you decide to use customers. In the first shard, you would place all customer records if the customer's name starts or database checks the first range-based shard, where function takes all the customer record values and produces one. We will store it in shard number 1, and if the hash function returns 2, we will store it in the shard 2. In the real world, these shards of course operate on a range of hash values that the function can return. The benefit of this approach is that it can produce even data distribution among physical shards. But on the other hand, since these hash values do not represent any business meaning, it may become challenging in the long run to reassign the hash values when item color lookup table ranges. The only problem you may pull at dating sites. This approach is very flexible. Each shard is meaningful representation of the. If the data access patterns are mostly based on geolocation, this approach works great. However, geosharding can also result in uneven data distribution. Now, let's talk about how to properly select a shard. Underloaded, it results in a process on all possible values for the shard key, storing specific data in a particular shard. For example, if you choose age as a shard key for a fitness website, most of the records might go into nodes for subscribers aged 30 to 45, resulting in database hotspots. Finally, you need to consider monotonic change. This is the rate of change of the shard key. For example, A feedback database can be split into 3 different physical shards. The first shard is for customers who have made 0 to 10 purchases. The second shard is for those with 11 to 20 purchases. And the third one is for customers with 21 or more purchases. As the business grows, customers will make more than 21 purchases, which will result in data hotspot in the third shard. That's the basics of the database sharding. Thank you for watching, and I'll see you